Vector databases. Introduction. Why do we need vector databases? Let's understand this with an example. Here is an image of a dog. And here are two different images of dogs. Both these images are similar. What about these two images? They are different. One is image of a dog and other of an elephant. As humans, we can easily tell how similar or different two images are. This is difficult for machines or databases to do. Traditional databases are not equipped to handle this. This is where vector databases come in. They give us a way to search by meaning rather than just a text or a simple number match. For this to work, source data, in this case images, is converted to vector embeddings, which are then stored in vector databases and indexed. This allows similarity search to be performed on them. Remember that any kind of source data can be represented as vectors and not just images. For example, words, which is useful in natural language processing. Here's a diagram that shows how vectorization is done. Source data is fed into an embedding model to convert it into vector embeddings that are then stored in a vector database, where they are indexed and available for search. So vector embeddings are simply an array of numbers. But why do we do this conversion of data to vectors? That's because machines can work with numbers easily. And what do these numbers in vectors represent? They represent various dimensions of the source data. As an example, in images, dimensionality refers to the multitude of features, color, texture, shape, etc. So each dimension corresponds to a specific feature. However, dealing with high dimensional data comes with challenges in terms of storage and computational efficiency. Therefore, to make high dimensional data more manageable, dimensionality reduction techniques may be adopted. These techniques preserve the essential information while reducing the number of dimensions. Vector embeddings are typically indexed inside a vector database to enable efficient storage and retrieval. Vector embeddings are organized in a data structure that supports efficient indexing. Common structures include tree-based or hash-based structures. The goal is to group similar vectors together to minimize the search space during similarity searches. So how is similarity search performed? This is done by finding distance between vectors. Vector embeddings that represent similar data will be closer to each other in the vector space. Vector representation of a cat will be closer to that of a dog compared to that of an elephant. Similarly, vector representation of a king will be closer to that of a queen compared to that of a tree. Metrics like Euclidean distance or cosine similarity can be used to measure the distance between vectors. Here are some examples of embedding models and vector databases. OpenAI, Hugging Face, Cohere provide us embedding models, and Milvus, ChromaDB, and Pinecone are examples of vector databases. Let's look at some common use cases of vector databases. Semantic search, which is search by meaning instead of a keyword match. Recommendations, power recommendation systems without depending on human filtering or tagging. Classify and cluster. Since similar vectors are closer to each other, this can help you find patterns. Anomaly detection. Identify outliers by looking for embeddings that are distant or dissimilar. Augment LLMs. Extend the capabilities of LLMs. We will learn more about this next. Let's take a look at an important use case of vector databases, where they help us overcome limitations of large language models by using a technique known as Retrieval Augmented Generation or RAG. So what are the limitations of large language models? LLM knows only what it has been trained on. Training LLMs continuously on latest real-time data is expensive and not always viable. LLMs do not have access to your proprietary or enterprise data. So proprietary data is converted to vector embeddings by an embedding model and stored in a vector database. Based on user question, relevant data is first retrieved from the vector database and then a prompt is created which is made up of the original user question and the retrieved contextual data. This prompt is then sent to LLM to generate a response. With this technique, LLM successfully generates a meaningful contextual response using proprietary data. Here's a list of popular vector databases and some traditional databases that also support vector search. So that was our introduction to vector databases.